Ever wondered how AI can guess what's happening in encrypted internet traffic? It sounds like magic, but it's actually a hot topic in cybersecurity. Today, we're breaking down a study that challenges some of the biggest claims about AI's superpowers in network analysis. Spoiler, some of those skills might be more trick than talent. Let's start with the basics. AI models like BERT, famous for understanding human language, work by turning words into math-based embeddings that capture meaning. Now, researchers tried applying this idea to encrypted traffic, aiming to classify what's happening without seeing the actual content. Sounds impossible, right? But some models claimed 98% accuracy, a number that raised serious red flags. Here's the twist: the study's authors didn't buy it. They asked, are these models actually learning patterns or are they cheating? Their answer: a big messy no. The team tested popular AI models by simulating real-world conditions. But here's the problem. Most previous studies split data packet by packet, accidentally leaking secrets between training and testing. It's like giving a student the exam answers before the test. Of course they'll score high. When the researchers fixed this by grouping all packets from the same session together, a per-flow split, accuracy dropped to 40%. Even the so-called best model, Pcap-Encoder, which focused on packet headers, didn't shine. Why? Because a simple neural network outperformed it. The lesson: complexity doesn't equal capability. The real kicker: when models were forced to truly learn instead of exploiting shortcuts, their performance tanked. This suggests they weren't understanding traffic patterns. They were spotting random correlations, like mistaking a traffic light's color for the time of day. So what's the takeaway? AI isn't a magic bullet. When evaluating these models, check for shortcuts, like data leaks or overfitting, and test them in realistic scenarios. As the study shows, even advanced models can crumble when the rules change. Next time you hear about AI achieving superhuman results, ask, is this a real breakthrough or just a clever trick? The answer might surprise you. Let's dig deeper. How do we even begin to analyze encrypted traffic? Traditionally, experts used deep packet inspection to peek inside data, but once encryption became common, traditional methods hit a wall. That's when machine learning stepped in. But here's the catch: early ML models didn't always learn the right things. Researchers found that many security systems were relying on shortcuts, like picking up on random patterns in data instead of understanding the real rules. Imagine a model that thinks a certain type of traffic is dangerous just because it's labeled that way in the training data, not because it's actually malicious. These spurious correlations led to wildly inaccurate results. Then came representation learning, a newer approach that's supposed to fix these issues. Instead of just memorizing labels, models now try to understand the underlying structure of data. But here's the twist: even this method isn't foolproof. Studies show that if you're not careful with your data, you can still end up with the same problems. For example, if your training and testing data overlap, or if your dataset has biases, like too many unencrypted packets, the model might fail in real-world scenarios. Let's break it down with two models, ET-BERT and Pcap-Encoder. ET-BERT was designed to analyze network traffic using a technique called pre-training, where it learns general patterns from vast datasets. But here's the kicker: when researchers reset its weights and retrained it from scratch, it performed just as well. That suggests it wasn't learning meaningful patterns. It was relying on shortcuts, like picking up on random noise in the data. Then there's Pcap-Encoder, which was built to analyze raw network data. In controlled tests, it outperformed some traditional models, but only when given custom features like IP addresses and packet headers. Without those, its performance dropped sharply. Meanwhile, simpler models like Random Forest or XGBoost, crafted by human experts, still beat it. Why? Because they're not relying on complex pre-trained features. They're using handcrafted insights from networking experts. But wait, there's a twist. When researchers removed IP addresses and other explicit identifiers, models fell back on implicit flow IDs like sequence numbers. This shows that even clean data splits can have hidden leaks, letting models exploit patterns that won't exist in real deployments. The solution: use a per-flow split, where entire data flows, not individual packets, are separated. This forces models to learn genuine patterns, not shortcuts. And let's not forget efficiency. Deep learning models like ET-BERT and NetMamba are way slower than simpler models. In one test, they lagged behind by orders of magnitude. It's like comparing a luxury car to a bicycle. Both get you there, but one's way more practical for everyday use. So what's the takeaway? AI in networking isn't a magic bullet. It needs careful design, transparent practices, and a deep understanding of both the data and the problem. Whether you're a network researcher or an AI enthusiast, these lessons matter. After all, the goal isn't just to build smart models, it's to build reliable ones.